Damping factor in an audio amplifier is the ratio of the load impedance to the amplifier source impedance. The whole concept first appeared somewhere in the 1940s, and even though it's impedance, which means frequency based, it's usually measured only at one set frequency at a fixed DC load like 8 ohms. So it is what it is. And there's your TikTok video. What, you're still here? The video's done. Why are you still here? I guess you want to know a little bit more about damping factor, huh? So do I. So let's dig in and look at a little more of what it is and why it is the most important, unimportant factor that you can look at. Yeah, I said that. A little bit of an oxymoron, isn't it? Let's check it out. Okay, before we can even think about understanding what damping factor is and why the heck it even matters or even doesn't matter, depends on what we're talking about, you really need to understand what a speaker actually is. A speaker is really a type of motor. And what is a motor? Well, it's also a generator too, but what is a motor and what is a generator? A motor is a device that can take electrical power and convert it into mechanical power. So most of the motors that we're used to seeing are rotational motors. So they take that electrical force and convert it into a rotational mechanical force. And a generator is just the opposite. It takes mechanical force and converts it into electrical force or electrical power. Now, the reason it can do this is because of the interaction between electricity and magnetism. That's why you hear the word electromagnetic field. Well, it's a combination of those two types of energy, electrical and magnetic. So this is a motor and a generator at the same time. It's a linear motor because the motion that it creates, the force, is linear. In other words, it's not rotational like a motor you see in a fan or something like that. It's the linear force. And just like it's a motor that will take that electrical power and convert it into mechanical power, and we can see that here real quick. If I hook up these wires to the speaker using a 9-volt battery, you can actually see that pushes the cone out, and if I reverse the polarity, reverse the leads on the coil, it pulls it in. All right, now you don't want to leave DC on a voice coil for a long period of time because it'll heat the coil up and could damage it, but it'll work just fine for that. So the speaker is a motor and a generator at the same time. Now, why do we say it's a generator? So I've connected the scope probes to the speaker terminals, and I'll see if I can get this all in shot so you can see what's happening. And I have my scope set to capture a single waveform. Now watch what happens when I tap the cone. Here we go, ready? And look at that. So as the cone was moving, it actually generated voltage. You can see the voltage that's there. And it's quite a substantial amount when you look at it because it went negative, and you're looking at about, well, I'm at 1 volt per division, so negative 1, 2, 3, about 3.5 volts. That's a good bit, right, for me just tapping the cone of the speaker. And then when it goes the opposite direction, we're off the scale here. So 1, 2, 3, 4 plus volts, more than 4 volts. And then you can see as the cone starts to settle down, the amplitude gets smaller and smaller. Now here's where it gets kind of interesting, because if I take my microphone off and I put it right here in front of the speaker and I tap the cone. Now I don't have anything connected to the speaker terminals right now. See that? If I put my microphone right here and I tap the speaker, Did you hear that note? Now, some of it is the frame of the speaker ringing. The lower note that you're hearing, though, is the actual cone of the speaker vibrating. Now watch this. If I take a wire and I short out the voice coil, so I just put a jumper across the speaker terminals, and I do my same test. Do you notice that? So I'll take one with So if what I can't do here is I can't show you when I tap the speaker with the jumper across there, because of course I would be shorting out my probes, right? There would be no voltage there. But let's say we could get inside there and measure this. You would actually notice that this ringing would damp very quickly. It would get damped and there would be less of it. In addition, this frequency here would be smaller. It would be a lower frequency and it would be a lower amplitude because we changed the whole characteristic of that speaker, because now you have that magnetic field, that electromagnetic field interacting with the cone. So you would have a higher frequency, so that these little pulses would be faster, and you would have less ringing. And that's what damping does. Now the amplifier, when you connect the speaker to the speaker terminals of the amplifier, an amplifier will have an internal impedance. Let's just say it's an internal resistance. I'll call it that right now to make it easier to understand. What it's doing is very similar to what I'm doing when I put this wire across here. Now there's different ways it can do it. It can do it passively by having an actual passive voltage across there, or it can do it actively, okay, by using negative feedback. Yes, the negative feedback circuit affects the damping factor. And the reason it does is anything that is not the original signal will feed back through that feedback line, which will activate the differential pair at the front end of the amplifier, and it will create an equal and opposite voltage, or not quite equal, a lower amplitude depending on the amount of feedback, a voltage that is opposite phase, 180 degrees out of phase of the one that this is creating by vibrating, and it will cancel out that voltage, which acts as damping. That's how it works. We'll look at that later in the video. Okay, we're going to do an experiment to simulate what the amplifier output section does to the speaker when you connect it. Now, for instance, a single-ended amplifier, or an amplifier that is push-pull but only has a single power supply instead of a differential, positive and negative power supply, it just has one single power supply. What will happen is the center point of that amplifier will be operating at about half of the rail voltage. So if you have a 60 volt power supply, the center point will be sitting at about 30 volts, and it'll go up and down from that 30 volts. I did a video on that, how that works. And the capacitor, they put a big capacitor like 1,000 microfarads or 10,000 microfarads, whatever, depending on the amp, in between the speaker and the output of the amplifier. And that will block the DC voltage, but it will allow the AC to pass. But it's a two-way street, okay? So what we're going to do is we're going to experiment. First, we're going to go back and do the first experiment again and look at the waveform on the scope. Then I'm going to connect this contraption, and all it is a battery, 9-volt battery, in series with a 470 microfarad capacitor. And we're going to just put that series circuit right across in parallel with the voice coil, and we're going to do our tap test a second time. All right, so let's go up here and let's look at this. And with nothing connected, just looking at the scope, we get that same waveform we were looking at the last time, right? Okay, so now I'm going to go down here and I'm going to connect this And you heard that little scratch sound? That was this capacitor charging up through the voice coil. So now the capacitor is all charged, and there is no current flowing here right now. So there's nothing there. So if I go to volts, and I go over here, and I measure from here to here, there is nothing there, right? It's 0 volts, okay? So, because this capacitor is charged now, so there's no current flowing. If there's no current flowing, there's not going to be any voltage across here. Let's go up here now. Take a good look at what this looked like with nothing on the speaker terminals. Now with that capacitor and battery there, watch what happens. Let's reset this. Let's tap the speaker again. Notice how it's damped. And it looks very similar to when I put that jumper across the speaker terminals, doesn't it? So this is kind of an example of how damping factor works and how it affects a speaker. And how the speaker can affect the amplifier, because of course the speaker, when we tapped it, remember that moving coil was generating power, correct? And that power would feed back into the amplifier. And the amplifier sees that as a power source, and the speaker sees the amplifier as a power source, and they both see one another also as a load. So they interact with one another. That's the most important thing we have to learn when we're trying to understand what damping factor is. Now, why do you think that capacitor and that battery in there, even though there was no voltage at all across these terminals, we measured that, why do you think that had a damping effect on the speaker? Well, it's all about changes in voltage and changes in potential. In other words, there's 0 voltage potential across here when the speaker's not moving. But when it's moving, it's producing a voltage. The voltage is different. It changes the charge of that capacitor from one side of the capacitor to the other, because the capacitor is 2 electrodes separated by an insulator, and they have opposite charges on them. So it makes it a capacitor. One will have a positive charge, one will have a negative charge, and because of that, they're in equilibrium until you do something to change that. When one side becomes more charged than the other, in one direction or the other, current's going to flow through that capacitor. And that's exactly what's happening. So when we moved that voice coil, we generated that small current, or that small amount of power. It actually made an imbalance on the 2 sides of the capacitor, and then the capacitor released its energy back into the speaker to make itself equal again. So it actually damped this circuit. Now, I don't want to get too far into the weeds with impedance curves and things yet, but I do want to put this little concept into your mind as well as we're looking at this. So I have my DATS unit connected, Dayton audio system. Okay, so what we're going to do is we're going to feed a frequency sweep all the way from 5 hertz up to 20 kilohertz. And then what this DATS unit can do is it can read back the impedance and phase of the speaker at each of those frequencies, and it'll plot it across here as a curve. You know, so you'll be able to see exactly what the speaker is doing at different frequencies. So let's click on that. And you can see, so this blue line represents the impedance of the speaker, or how many ohms the speaker is appearing to be of a resistor at that frequency. So if we look clear down at 5 hertz, you can see right there's 10 ohms, and all the way down here is 5 ohms. So it's about 7 ohms right there. And so anywhere between here and here is pretty normal. That's within that 8 ohm range. You're going to be floating around in here. But take a look right up here somewhere. We get about to here, this area. right around 46 hertz, if I zoom you in a little bit, you can see the impedance goes way up. And that's because we're reaching the resonance point of that speaker, where the mechanical properties and the electrical properties of the speaker are kind of falling in line with one another and canceling out. And it makes it look almost like an open circuit, or like a much higher impedance circuit, let's say. And then as you pass through that point, you can see they kind of get out of kilter with one another, and now the actual voice coil starts taking over again. And then as you get up to higher frequencies, the speaker can't react to those higher frequencies. So again, the impedance starts to go way up again. It'll climb. And the higher the frequency, the higher that'll climb up. So you can see that. Okay, so take a good look at that. Now I'm going to go down here, and I'm just going to take a piece of cloth. I'm just going to lay it right there on the cone. So that has weight. So it's actually adding some damping to the cone. Watch what happens. We're going to do another same sweep again. And look what happens. It changes that, right? Now you can still see we're still at that area. It's still resonant at that area. But look how much it has damped that out. And this is starting to get into things like box properties, for your speaker enclosure, and the crossover and all that stuff will affect all these things. But also having that damping factor in the amplifier will do a similar thing to this. Okay, so we have the AccuPhase set back up here, because that's going to be kind of the subject of our little experiment. But before we get into it, I'm going to just tell you right up front that, number one, I'm going to debunk a few things that are kind of popular on the internet. And probably I may say some things that some of you may disagree with. Because really, this is such a subjective thing. On one hand, you got people that come in and they say, oh, damping factor of 10 is enough, and it's good, and I like the sound of tube amplifiers, and the tube amplifiers sound good with low damping factor. And then the next person comes along and, no, you have to have really high damping factor. The higher, the better. It controls the speakers better, and it keeps them from oscillating, and it... Well, you get the point, right? Who's right and who's wrong? Well, honestly, you're going to find out that those things really don't matter, because the number that you see in a service manual, for instance, if it says this thing has a damping factor of 50, and they'll give you some arbitrary number, at 1 kilohertz into 8 ohms, that tells you absolutely nothing about the characteristic of the amplifier. Really, what we want to know is how the amplifier controls the speaker. The other thing is, how can it be that a tube amplifier with low damping factor can sound as good or better than a transistor amp with high damping factor, or vice versa? Well, part of it has to do with the speakers you're using. Now, the experiment we did with the speaker earlier, that had a rather stiff compliance to it, meaning that the speaker, the suspension of the speaker was a little bit stiff. You had to kind of push on it. It moved a little bit, but if you get one of those big foam surround high compliance speakers, if you tap on that, they really move. They have a lot of travel to them. They call that excursion. So they have a really high excursion, and it doesn't take a lot of physical force to move them. And those ones tend to need a higher damping factor to control them. Now, of course, with acoustic suspension, you take that high compliance speaker and you mount it in a sealed enclosure, an airtight box, and the air actually acts like a spring. It kind of pushes against that cone to keep it from being so high compliant. And therefore, that's why you look at the old tube gear, they will always have speakers that have really stiff suspensions on them. And they're in very large volume cabinets. And it's just a completely different way of designing a speaker than when you look at some of the modern speakers you see today. It's completely two different subjects. So really the amplifier has to be properly paired to the speakers. Not every amp sounds good with every speaker, and not every speaker sounds good with every amplifier. And that's, I think, where a lot of these discussions come from, the differences. So if you think you're going to come out of this video saying a damping factor of 100 is ideal, I'm not going to tell you that. Now, the second thing we're going to talk about is how to measure damping factor. Because I see some procedures floating around on the internet, and they're not going to work. And we're going to set that test up right now and do it. I'm going to prove to you that you really can't measure damping factor as easily as you might think. Now, there are some more modern pieces of test equipment that can actually calculate it, somewhat and measure it. But it's not something you can just do with a voltmeter and an oscilloscope. Okay, that takes a lot more than that to do this. So let's kind of look at what I'm going to talk about. So the method that you read about online is called the voltage drop method. And the story kind of goes like this. The first thing you do is you disconnect the speaker load from the amplifier. So if you go over here, here's the speaker load. Okay, these two are tied together, these two are tied together. This is just an extra set of test points to hang your meter or whatever test gear you want. These are where we actually plug in to the resistors. They're in parallel though. So anyway, I'll unplug this, and that'll remove the speaker load from the amplifier. Okay, and I'll make sure nothing's shorted out here, because that would not be good, would it? And then I have this meter. Why am I using an analog meter? Well, because it's a little easier to see. You can use a digital voltmeter, or work just the same. This one will work good at 1 kilohertz. And I like the needle because, when you have an analog meter like this, it kind of damps the movement of the meter, so you can actually see, it'll kind of average it out, so nothing kind of bounces around. So first thing we're going to do is we're going to turn the amp on, which it is on. And we're going to feed a 1 kilohertz signal into the amplifier, just into the auxiliary terminals. And then we're going to turn this up until we have about 10 volts. Why 10 volts? Well, we don't want to drive the amp into clipping, but we want to have enough power that you can actually see a good deflection on the meter. 10 volts for this amplifier, because this is a 100-watt amp, is going to be, it's going to be a nice amount of power, but it's not really pushing the amp hard. So what you're supposed to do is you adjust the voltage, or the output of the amp, till you get your 10 volts. Remember, there is no load on the amp. The only load on the amplifier right now is this meter, and being 8,000 ohms per volt full scale, if we're on the 12 volt scale, what is that, 72 or 96 volts, or 96 kilo ohms? So it's almost 100 kilo ohms. So right here's 10 volts, where it says 100 there. That's the scale we use. I'm trying to look straight on over the camera. We're pretty close. Okay, I would argue that we're pretty close. And we're not hurting the amp right now, because really it's not driving any power. This is just open circuit voltage. So you can see we have 10 volts there. Now what I'm going to do is I'm going to turn the signal generator off to take that signal away. All right, so that's the first thing I want to do. I'll make sure this is right on 10 volts. I'll turn the signal off like that. And now I'm going to go over here and I'm going to connect the speaker load. Now, here's the thing. When we do this, in theory, what should be happening is we are putting the speaker load in series with the amplifier load. How is that? Well, let's do a little doodle drawing. So you have your amplifier. Okay. And your input is your signal input. And this is your speaker output and ground. So this is where your speaker would go. And between the power supply and the output section of the amp, okay, it's going to have a certain resistance. And that's going to be called your output impedance. And we're just going to look at it as a resistive value. And this is usually going to be very low in, milliohms. And then when you connect your meter, you're just reading the open terminals. So you're just going to read something with no current, so you really don't know the voltage drop across this resistor. But then what we'll do is, after we set this for 10 volts, we're going to put another resistor in here, and that's going to represent a speaker load. Let's say it's 8 ohms. Now, if this internal resistance was 8 ohms and this was 8 ohms, you'd have a perfect divider between these, and half of that voltage would be here and the other half would be here. So you'd have 5 volts here and 5 volts there. If these two are equal, remember, damping factor is the ratio of the amplifier output impedance to the load impedance. If it would be 1-to-1, then your damping factor would be 1. That's how it works. It's really simple, at least on the surface, huh? So theoretically, if this has any resistance at all, any appreciable amount of resistance, when I put this load on here, I will read what portion of that 10 volts is dropping across this resistor, and then whatever's left over has to be what's dropping across this resistor. And those two resistances are going to become your ratio for your damping factor. Does that all make sense? It's not that hard to understand when you look at it that way, right? So really, I'm going to connect this 8 ohms. Anything that this absorbs is going to be eaten up by this internal resistance, or internal impedance is what I should say. It's actually a Z. This is R because I have just a resistor on there, but in the real world, this would be a speaker, and its impedance would change with frequency. Okay? Just kind of like this does in here, because there's some things in here that can make that happen as well. I won't get into that yet. So we set this for 10 volts. This is 10 volts right now, and that's going to be V open, or open circuit. And then we're going to find out what V across the load is. It should be less than 10 volts, right? It should be 10 volts minus what it drops across here. So we're connected. I'm on the meter. I haven't changed any controls, anything at all. Let's turn this back on, and we should see our voltage drop. What happened? It's right where we left it. You see that? It's right on there. Now, you might say that, well, Tony, it's a tiny little resistance, so you don't see the voltage drop. Well, that's true. That's exactly true. But more importantly, that's not the resistance. That voltage drop is not a result of that resistance. And I'll show you why. Okay, let's look at one of the output sections in this amplifier. Right here is the speaker output. There's your snubber network and your Zobel network. See that? And these go out to your speaker terminals. Actually, this goes through your speaker protect relay first, and then out to the speaker terminals. But right here are your outputs, your 4 big transistors. These are the big transistors on the heat sinks. And if you look, the power supply goes straight into the collectors of these resistors. Your positive goes into the collectors of the NPNs, and the negative voltage, it's negative 55, goes into the collectors of the PNP transistors. And then the emitters are what join together at each side at your speaker terminals. And by having equal and opposite voltage, bias voltage on these, they cancel out, and with no signal, you would have 0 volts here. But you have these emitter resistors, and look, these are each 1 ohm at 3 watt. Do you see that? So there's 4 of them. So there's 2 here, and they're in parallel. So that would be a half an ohm here and a half ohm here. So theoretically, the output impedance should be around a half of an ohm or more. And of course, if we had a half of an ohm voltage divider with 8 ohms, you would see a bigger drop than you just saw on that meter. So how is that possible? Sometimes the voltage will actually be a little bit higher when you connect the load. How can that be? I'll let you think about that for a second. Well, the reason that that is happening, you have to go all the way back to the front end of the amp. And if you look, your speaker terminal doesn't just go out to the speaker, but this center point also goes all the way back here through this resistor and into this differential pair. This is your input pair. This is your negative feedback circuit. So it will feed some 180 degree out of phase signal into this little first stage amplifier here, which is actually not much of an amplifier. It doesn't really amplify anything. You don't have voltage amplification until you get further along. But it will cancel out some of the signal that's coming in here. So this is a feedback loop that can dynamically change the gain of the amplifier. So when you put that load on there and it senses that the output is trying to drop, this will throttle down and allow this to let more of the signal through and will compensate for it. So essentially, if you have an amplifier with a negative feedback, I don't care how little bit of feedback, it's going to pretty much cancel out any voltage drop that you would see from the internal resistance. So really, the damping factor is more greatly affected by the feedback circuit than it is the actual resistors in there. Do you see how that can be? So damping factor mostly is a function of your negative feedback. And here's the thing, when you put a speaker load on there, back to here again, that feedback circuit is picking off of right here, right where it goes to the speaker terminal. And you got this feedback, and this goes clear back into your input pair. That's your input. See that loop? And in some really high-end amps, which you don't see it very often, they will actually have another wire, a sense wire, that'll come out of here and go all the way over here and actually connect to the terminal here. And what that will do is that will cancel out the effect of your speaker wires too. It works kind of like the Kelvin leads do on your 4-wire ohm meter does. Remember how we have some of these ultra accurate ohm meters that have 4 wires? See, with the probes with 4 wires on them? That's similar in principle to what's going on here. It's using a sense wire and a servo circuit to basically cancel out any of the losses you would have or any of the distortion that would be in there due to the speaker leads. Now, again, very boutique. You don't see that very much, but that's the extremes you can go to. And even with low damping factor, when you have things like this going on, even a damping factor of 1 will do wonders for the speaker, as you saw in there. So I could have taken an 8 ohm, for instance, that big speaker we tested out was an 8 ohm speaker. I could have put an 8 ohm resistor across the speaker terminals instead of a dead short, and it would have almost done the same job of damping that signal out as the dead short did. Very little difference. It's diminishing returns as you go along. So as you can see, damping factor is more of a function than it is a measurement, because it's a moving target. It's something that changes with frequency. It's something that changes with the speaker load that you put on it. It changes with the impedance curve of the speaker, because a speaker will react differently at different frequencies. Now, just to drive the point home a little bit further, I want you to look at this. It's still sealed up. Look how many turns of wire it is. Very thick enamel magnet wire. But look how thick the turns are. How many turns are in there. That's a whole ton. This is a 1.2 millihenry, and it's a 0.33 ohm coil. This is a typical coil you would see in a crossover network for a woofer in a like a 3-way speaker system. Rather big. Look at my hand. It's a big coil. And by putting this in between your speaker lead and your amplifier and the speaker itself, you're adding another, just in DC resistance alone, you're adding another 330 milliohms, if you can see that on there, which kind of throws the whole idea of low output impedance right out the window, doesn't it? It really doesn't make a difference. As soon as you put your crossover in there, as soon as you put this piece of wire in here, I don't care how fancy, you could buy $30, $50, $100,000 wires, and they're still going to have some loss to them, unless you use a 4-wire servo system like this, which will kind of cancel that part out, but it's still not going to compensate for this. But it doesn't matter. The reason it doesn't matter is your feedback. It's all about the feedback circuit. Now, some purists with certain vacuum tube amplifiers will completely eliminate the whole feedback circuit. So this won't exist in there at all. And by not having this, your open loop gain will be the same as whatever, because there is no closed loop, because there's no feedback. The only feedback you'll have in those kinds of amplifiers is feedback that's naturally occurring in the circuit itself, which is very low. And there are arguments for that. If you have a speaker with a very low compliance, with a really stiff suspension in it, you don't need to have that kind of feedback. So this is where you hear a lot of people who are more into vacuum tube amplifiers will talk about low damping factors, because really the only damping factor you have then is going to be the output winding of the output transformer itself, which actually is going to give you a damping factor usually above 1. Somewhere 1 or above. So you still have damping factor there, even with no global negative feedback. I'm throwing a lot of terms at you all, but I'm sure a lot of you have heard these terms before, but just didn't understand how they all interacted with one another. But I hope you understand now why it really doesn't matter. Now, then why do people go through all the hassle of making an amplifier have a damping factor of 1,000, or I've seen them as high as 4,000? Well, they build the amp to have an extremely high open loop gain, then they squelch it way down with lots and lots and lots of feedback, and that gives you a whole ton of headroom to work with different things like very dynamic impedance curves It gives you a lot more latitude with the little network in here where you have the capacitor and the resistor network that goes to ground at your input here, you know, from your feedback. It allows you to adjust for those things a little more. But again, that high number in and of itself isn't what makes the amp good or bad. It's just part of the circuit design that they're using for that amp. Having an amp with even more feedback doesn't necessarily mean it'll be even better. More is not always better. These are very carefully planned out and tested under different loads, under different impedance curves with different types of speakers. So it's really pretty important that you get all that correct when you're designing an amp. A lot goes into it. And that's really why I don't care about damping factor. And when all of you, I've heard a lot of comments, why don't you put a reactive load instead of just a 8 ohm resistor on an amp when you're testing it? Because then you're chasing a moving target. That's why. It's unpredictable. I can actually look at the output curve, like if I do the frequency analysis program on my scope up here, and you've seen me do that before with that scope, I'm actually putting a whole swept set of frequencies through the entire audio spectrum into the amplifier across that resistor, and I'm reading back what that amplifier is doing under those conditions. Now later on I can go to a fixed frequency and I can add reactance by putting like a 1 microfarad or 470 nanofarad capacitor across the speaker terminals with the load and see how the amp deals with it, because that's gonna add a signal that didn't originate with the amp, right? So the feedback circuit should be able to deal with that if everything's working properly, and it usually does, because again, these are things they cook into the recipe when they're making these amps. So last but not least, what happens, because remember this amplifier has that little switch on the back. So looking on the back of the amp, you have this little knob and it has 3 positions: normal, medium, and soft, I think is what it says. Yes, normal, medium, and soft. And theoretically, they're claiming that this has, when it's in normal mode, it has a representative damping factor of somewhere around 50 or 60, something like that. Normal would be a damping factor of something like 10, and soft would be a damping factor of 1. I think that's what it says, and again, if I'm wrong, I'll try to look it up in the owner's manual and give you the actual numbers. But this affects the damping factor by changing the amount of feedback. That's all it does. It's not adding resistors or anything into your output of your amp or taking resistors away, but it's actually just changing the feedback circuit in the amp. Let's see what that does. Okay, I'm going to kind of get this at right the center of scale. This is on a 12 volt scale. So I'm going to run this up to about 6 volts, which is right here. I'll get it as close as I can, eyeballing it here. It's right about there, right? There's 6 volts. Now, right now, that damping knob is set to normal mode, which is the highest damping factor that the amp is designed for. If I rotate this control, notice what happens when I set it to normal. It actually has more output. Instead of 6 volts, it's about 6.3 volts. And if I go to soft, it goes even higher. See that? And really, by reducing the amount of feedback, it allows more of the signal to get out to the speaker terminals. That's what that damping factor knob does. It just changes the feedback. So Do you remember when we did the Booty Fab Labs amplifier series and we played around with that feedback resistor? What was it? I don't know, it was like 30K or something like that. I don't even remember what value it was. And we were changing the amount of output of the amplifier. Same thing on the phase linear, because some of the changes we made, we had to adjust that a little bit. That's what we were doing, and by either giving more feedback or less feedback, it allows more or less of the signal to come out. And there it is. If I go back to normal, it'll drop back down to 6 volts. So that's all that it's doing, but there's a lot more going on than just that. It doesn't just make the amp louder or have more output, but because a damping or the feedback circuit consists of resistors and capacitors, you see this 100 microfarad 10 volt and this resistor right here, you're actually going to change the profile of how this feedback circuit works. So you're actually going to change the response curve of the amp as well. But in order to see that, you would need to do a frequency analysis on this. You can't just see it at one set frequency. All it'll look like is that the amp's getting louder or softer depending on where you set that control over here. And this is the damping control here. All it's doing is switching in different resistors to this feedback circuit where it comes in here. It's like changing that. Now the whole point of this is if you lower the damping factor of the amp by changing the feedback circuit, it should more closely mimic what a vacuum tube or some of the older amplifiers sound like, or what their characteristic is. So let's say you wanted to drive a really old, like those old Jensen big speaker cabinets, you know, or some of the older the JBLs or the Electro Voice, you know, all those different kinds, some of the older Altec speakers. A lot of those had really stiff suspension drivers in them. And they actually worked a lot better with lower damping factors. So they may sound better with a lower damping factor, because really when they designed those speakers back then, they were designed to work with vacuum tube amps that had relatively low damping factors when compared to a modern transistor amplifier. One last little note, if you're dealing with Class D amplifiers, guess what? You're back to the lower damping factors. Now, there are, again, boutique amps that are different than that, or ones that use a lot of feedback. But because you have that high frequency carrier signal in a Class D, you have to be able to cancel that out. You want to filter that out. And the filter network is, again, is an inductor. It's a coil that is used to filter out the high frequency oscillator circuit of the Class D amp. So guess what you just did? You just added more resistance into the output impedance. And again, unless you compensate a lot for that by negative feedback, you will see that Class D amps will probably have a little bit higher damping or lower damping factor than the older transistor AB type amplifiers, you know, that came out before it. So again, back to my TikTok video. Damping factor is the ratio of the output impedance of the amplifier to the load impedance that you feed on it, but because that you connect to it. But because it's impedance, that means everything is controlled by frequency. As the frequency changes, so too will everything, damping factor, everything, because it's a moving target, which is why I don't really care about damping factor. But if I use the term damping factor to describe this will increase or decrease the damping factor of the amp, I'm only saying that it will allow it to have a little more or less control of the speaker damping. That's all. All the other things, you know, all things being equal, that doesn't necessarily mean the amp's going to sound better or that it even needs that. Hope that makes sense. So that's it. Again, if those of you who thought that we were going to hook up some sort of special meter and it would tell you what the damping factor is, and then you could say, well, it's 100, so it's good, or it's 10, so it's bad, or whatever. Well, I'm sorry. That's kind of my opinion on all this and my take on it and my understanding of it. Again, I'm not a genius. I don't know everything. This is just my own hobby and, from my experience with it. But hey, in the comments section, that's why we have comments, so that we can share information with one another. So feel free to comment down there below and let me know what your thoughts are. Until next time, I wish you all peace, joy, happiness, and good health in your lives, and hope to be back real soon with another project. Take care, everybody. Bye-bye.